Hello everyone, I am David. I'm going to talk about peer-to-peer algorithmics or peer-to-peer algorithms. I'm not going to talk about specific software, so we're going theoretical today. I'm from Sweden, I should mention. I do understand German too, so you can ask questions in both English and German, but I will answer you in English. I have researched peer-to-peer algorithms since 1997, and in autumn 2000 I went full-time. That is, I do what I do every day full-time. I research peer-to-peer algorithms since 5 years back. The good part is I'm finished with my research this summer, so now I'm going on to implementing my stuff. That will take another few years. I should mention, since everyone asking, okay, try this one. Does this sound better? What do you think? Okay, I'll remove this one. Give me a second to remove this one because it's not comfortable. So people in the last row, can you hear me now? Good, yeah. What? What? It's on. Can you hear me? Okay, I'll talk on. Can you hear me now? Okay, next one. Everything to get me nervous, obviously. Good. Now I lost my track, but what I'm doing now, since I've been a researcher for 5 years to solve these problems in peer-to-peer algorithmics, now I'm doing a peer-to-peer programming library. That is a module that other programmers can use to make peer-to-peer applications. So you don't need to do the research, you just use my nice library when it's ready. And also, as I said, you can ask questions in both English and German. So let's go on to the next slide. Well, the first slide. This is what I think about ideal peer-to-peer systems. This is what I want a peer-to-peer system to do or be. The first one is I want them fully distributed. That means that all nodes, all computers in the network should be more or less equal. That is, everyone is helping out, providing bandwidth and whatever resources you need, and everyone is probably also consuming resources. Of course, some more CPU and stuff like that, and I don't mind if they help out a bit more then, of course, but basically they are equals. Also, I want them totally serverless, and serverless, that's the key word for my research. That is, I don't like servers because they cost money, and they can break. So in my systems, my algorithms, there's no central computer whatsoever. No one is boss. Not even one of the peers are voted a boss. They're totally equal and self-organized. So no leaders. I dislike leaders. There's a nice side effect of that, because if I have no servers, I have no costs. So I can have 1 billion nodes and 0 cost. And I can turn off my computer at home and go to bed. I want them fully scalable, and that means that they should be able to grow to millions or even billions of nodes without getting problems. So actually my algorithm works up to many billions of nodes now. I want them globally searchable. That is, if you're looking for something, a person or a file or a chat room or whatever the item is you're looking for, then I want you to find it, even if there's, say, 1 million nodes and only one node has the item you're looking for. I want you to find it. It shouldn't be like it's beyond your search horizon or something like that. I want them, of course, to be bandwidth efficient. Not every user have multi-megabit connections. Some users are still on normal 56K modems or even slower. I want them to be robust, of course. I don't want them to crash and stuff like that. I want the network to go on whatever happens. Encryption, of course. I don't want other people to listening in what we're doing. Stealthy means that if someone is listening to your communications, they shouldn't be able to detect what kind of application you're running, preferably, or at least not what you're doing. And the last one, well, it would be nice if they're anonymous. And that's actually the easiest of all those, I think. You can make them anonymous too. But most of the algorithms I'm going to talk about are not about anonymity. But even anonymous networks that needs all those peer-to-peer algorithms to work. Yeah, when I did my research, I kept in mind some target applications. That is, what will I use these algorithms for? So what application, there's a bunch of applications I had as example applications. And then I figured out what kind of problems do they pose? What do they need to do? What kind of communications? And so on. And then that meant I know what problems to solve and what algorithms I need. So this is a short list of that. The first one, everyone knows, file sharing, of course, very popular. That's actually the last one on my list, really, but I put it on the top to make it easier for you. Chat systems. Most of you know about IRC or some other chat system. We can now do that totally serverless. We don't even need DNS system, by the way. And it means you can chat with other users within a network using those algorithms, and you can find the chat room and users to chat with. Instant messaging, too. That is, connect to another user and send him a message, more or less immediately. Internet telephoning, that's really the same problem. Find the user and connect to him. Then if you send him a short message or sound, that doesn't matter for me, really. It's to find and connect, that's the problem. If there's 1 million nodes and he's out there somewhere, how to find him. Internet gaming. Internet gaming is really all the other ones above in one package. It means you need to find the game network. You need to have a chat room where you can go in and chat with other gamers. Then you need to start a game, and a game going on is more or less like a chat room. Everyone in the room hears and sees what other gamers do, what moves they do, and stuff like that. Then radio and TV, broadcasting, or as some people call it now, peer casting, since it's peer-to-peer. That means you have your, for instance, your own little radio show at home. You have your little DSL connection, just say 500 kilobits. But then your radio show gets very popular, and suddenly 1 million people wants to listen to your Friday night show. And that's used to be a problem, because usually you had to send the sound once to every listener. But that's not necessary. You can actually have the nodes listening, helping each other out and send the message, the sound on to the other ones. So actually, with a normal, slow, modern broadband connection, you can have 1 billion radio listeners. And in some years, when you have 2 megabits, because TV picture, that's about 2 megabits, then you can have 1 billion viewers of your Friday night talk show. So I hope someone of you will start some really good talk show someday and test if it really can manage that many users. And of course, distributed calculation systems, like everyone heard about City at Home, perhaps. There are a project currently calculating HIV medicines, protein folding calculations. That is, lots of computers help out, connect together, and do the calculations. Nowadays, those systems use some servers to organize this. And now we can do it without any servers. And there's lots more things you can do. But this is the kind of stuff I kept in mind when inventing my algorithms. This is what I call my scary picture. It actually did scare the shit out of me when I made it first time. There is like 2 approaches to peer-to-peer algorithms. I'm an ex-machine engineer. When I build a car, I worked for Volvo in Sweden. We have one part solving each problem. We have 4 wheels, we have an engine, we have many parts, each solving some problem. And when I build software and research, I think the same way. There is many problems, so I have one algorithm solving each problem. Sometimes, if I'm lucky, one algorithm may solve 3 problems. If I'm unlucky, I need 3 algorithms together to solve 1 problem. So that means these are many modules that together solve all the problems to run most peer-to-peer applications. But I noticed university researchers, they tend to work another way, because they're not ex-machine engineers, not ex-programmers. They want to find the algorithm that solves it all. So they make one huge algorithm that solves most of the problems, not usually all of them, but mostly solves all of them pretty bad. So I just wanted to show it's lots of algorithms and modules together. And that's not the complete picture. It hasn't the crypto part. Because then I would need 3 dimensions. Okay. The first question everyone is asking me is the question about this. So that's kind of almost my first slide. So I'll answer the first question that everyone anyway will be asking me. If you have a serverless network that's used no servers, not even the DNS systems, how are you going to find the network? That's called bootstrapping. You need, of course, if you can find one of the nodes in the network, then of course that node can tell you about other nodes, and those other nodes can tell you about other nodes. So you need to find at least one of them. So how can we do that? Oh, sorry. Well, there's 2 approaches, of course. The old one, old style, you can have a server on some fixed IP number or some domain name, so you look it up in the DNS system. But that's, of course, centralized and server-based, and that's not nice. So there is the serverless way to do it. Well, really what I do, when a node is on the network, it collects addresses of other nodes, and it also collects addresses of good nodes, that is nodes that is often online with the same IP number. And for me, a good node isn't a good node that is online 24/7. That's not necessarily a good node. A good node is a node that is online every now and then, say 1 hour a week, that's nice, but with the same IP number each time. So if a node is online 1 hour a week, that means it's online 4 hours a month. And if you collect thousands of such nodes, the next time you're going online, at least some of them will be online the next time too. So I collect thousands of good nodes and store that in a little file on disk. And next time the program uses that file and tries to connect to the nodes in that file, and hopefully some of them will be online and you will be connected. Now, of course, if it's the first time you run the program, you haven't been online and collecting nodes before, well, there's some simple solutions to that too. First of all, when you download your install package from a website or you get it on disk from a friend, you get the executables and you get your start list. So of course there's a start list included in the package, a list of good nodes. If your start list is too old, for instance the install package is very old, or you haven't been running the program for a year, then of course you need a fresh start list. But it's just a file, so you can go out, download it from some website, or you can go to some chat room, ask people, does anyone have a fresh start list for me? And if you can't do that because it's for some reason perhaps illegal or controversial, you can call your friends and ask them to come over with the disk too, with the start list. Now, I have a question. Oh, okay, sorry. I was hearing myself too much, but okay, good. He wanted me to speak closer to the microphone. Yeah. I do an additional trick with the start list. I actually store it in HTML format so people can publish it on their website if they want to help out, so people can get fresh start lists if they need it. But that's how to solve that problem. It's a well-known solution, but not everyone knows it. And it has been tested by many networks, so we know it works. Okay. When we design algorithms for peer-to-peer networking, we need to keep in mind some problems with the internet. The kind of problems that researchers tend to forget about because they are uncomfortable. The first problem is high node churn. That is, nodes, home computers, they tend to turn them off when they leave their home or when they go to bed, or they crash and stuff like that. Well, I know Linux people, you have your own computers online 24/7, but that's just part of the world that does that. That's one problem. The other problem is that there's firewalls and NAT routers that is not properly configured. So many nodes can't receive incoming TCP connections. They can only do outgoing TCP connections. So that we have to keep in mind. And then there's the worst problem of them all, and not many people know about this. Actually, not all computers on the internet can reach all other computers. For instance, I myself, I live in Sweden. I can't reach northern Lebanon, but I can reach southern Lebanon. And that is due to a bad router in southern France. I traced it to that. It's wrongly set up, so between Sweden and northern Lebanon, no routing. And that's common. So I say perhaps every home computer in the world can reach perhaps 98% of the other home computers. We normally don't notice that because web servers are in server hosting sites, and they're normally more reachable, because if they aren't, people complain and the people taking care of routers fix it. But so not everyone can reach each other, and sometimes it's because of badly configured routers, sometimes it's because there is congestion, too much traffic in some area. Okay, network layout. So how should we connect these nodes? How should we organize them? Well, there are some approaches. This is the simplest of them all, a two-dimensional grid, very simple to understand. Unfortunately, it's actually pretty bad to code, because you have to take care of lots of exceptions, like if you see it's a hole in the network there was a node there and it left some minutes ago. So now we have a hole. We have to repair that hole in some way. That's lots of code and means lots of messaging between the nodes to fix that problem. So, and also it has a problem since it's two-dimensional. The distance from the nodes in the corners are very far away. So if you send a message out on the network, it will take a long time before it reaches the other corner. So that's bad. The other one, very popular, many networks use it today, is a hypercube. It's actually, well, it's a multi-dimensional grid. It's not two-dimensional, it's x-dimensional. And you connect them, well, if you don't know hypercubes, I shouldn't explain them, but it's lots of connections, but in a well-ordered manner. And it's very easy to understand once you understood it. But it has the same problem with lots of code. It's tricky to code, and it's tricky for the network to maintain the order. It means when nodes disappear, you have to fill in the holes and stuff like that. So it's lots of messaging and lots of code, but easy to understand. And it's nice, it's short distances. There's no really corners. There's no node that is very far away. So messaging is quick. And here comes my favorite, the random network. Small world networks are similar, but in random networks, you just connect to a bunch of other nodes, randomly chosen from the whole network. So you just pick 5 nodes, any nodes, and connect to them. That means the network looks like a mess, of course. And understanding how to handle it is a bit tricky. Human brains don't understand these kind of things very well. We don't like chaos. Well, you do, you're a case communication club, but... but once you understood it, the code is very nice. Some of the algorithms are actually just 1 page of code, and it works. So it's very, very easy to implement once you have a good algorithm for it. But it takes a bit more to understand. And also, like the hypercubes, very short jump distances. Actually, shorter jump distances than hypercubes. So this is more efficient than hypercubes. This is not the most efficient structure, but the second most efficient structure there is, as far as we know. Small world networks have been written a lot about. The difference between a random network and a small world network is only that in small world networks, it's slightly clustered. You have some of your links are to nodes nearby in some way, geographically nearby, or your friends or something like that. But at least to make a small world network work and be a small world network, you have to have at least some random link to connect to the rest of the world. So from an algorithm point of view, when we put stuff on top of it, a random network and a small world network is more or less the same thing. Yeah, random networks, and to some extent also well-ordered grids and stuff like that, has one main problem, or well, problem number 1 on my list, so to speak. It's net splits. That is, they tend to kind of split into islands and fall apart into many small islands. Most people are unfortunately not aware of this, so they build networks and then they fall apart, and they, this is weird, it falls apart. Then they plug in a bunch of servers to keep it together. Kazaa did that. When their servers go down, within some hours, their network starts to split into islands. And after 1 week, it's so many small islands that you can't use it anymore. But there's ways to solve this. In this case, it's random networks. So the simplest way is do it the Gnutella way, the Gnutella network. They use what I would call a node address announcement. Each node, now and then, sends a little message that is jumping out over the network, more or less randomly, announcing, here I am, I'm this node with this IP number, and you can connect to me. And it jumps, say, 10 jumps away, randomly. And that means that after some time, many of the nodes within 10 jumps from you know about you. So when they need to make new random connections, they can connect to you or someone else who have sent them an announcement. This has one big problem, that your messages just goes tops 10 jumps away. So when you choose new links, all those new links will be within the 10 jumps closest nodes. So that's some clustering. That means if you do it wrong, it splits. So then a better way is to use a random walker. That is, each node has one separate connection that they use just to connect to nodes and walk around in the network. So the first 10 walks jump you do is like the address announcement is jumps 10 jumps away. But when you have jumped 10 jumps, when you go another 10 jumps, it means you will be further and further away. You won't be jumping around in your close to yourself. You will be walking far away over time. So that makes it much more random. And that means that the links between, let's say like these two islands, if some node that wants an extra link, it's a big probability that the new link will be across to some other island. And in that way make the island less of an island. I call that my island ripping effect, because it rips islands apart or really rips them together. And there is a third solution that's unfortunately I don't have the time to explain, but it's similar to random walker but even more random, and that's what I call a chaos net. It's actually a network in itself, but it's more efficient and more random, more perfectly random. I like perfect randomness, it has some advantages. Yeah. Next problem is flooding. Too much work for a node. Too many trying to connect to it, or too many trying to send messages through it, and so on. Congestion, really, as we have on the internet also. And there is some solutions to that. One is to have round-based algorithms. Like in your algorithms, everything that is done, say, once a minute. So you exchange data with other nodes, say, once a minute, and you never do more than that. And that means the ones you're talking to, you don't load them more than once a minute, one message per minute. So that kind of keeps the messaging a bit more controlled if you design your algorithms so they work round-based. Another way is to use throttling. That is, if you get too many messages, you just refuse to work. You start throwing away messages and don't send them on. So if someone's sending you a message and asks you to forward it, you just refuse, because I can't do more work. So that's what I call throttling. It's primitive, but it takes care of the really bad happenings when too many nodes are sending you messages. And the third one is randomized algorithms. That is, if you use a lot of, I say that peer-to-peer networking is chaotic. It's lots of chaos. Nodes going online and offline. They are in different parts of the world and so on. And if we can instead use more randomness, we make it even more random, then things start to smooth out. You know, if you throw a dice many times, 1 million times, you get about as many ones as twos as threes. And we can apply this on peer-to-peer networking. So first make it more random, and then when it's random, it's smooth. And when it's smooth, then you can make order on top of that. Yeah, so let's look at one algorithm that runs on top of a random network or a small world network, or even some other network structures. And this algorithm is actually both round-based, throttled, and randomized. So it's all three of them. And it's what I call throttled, balanced, slotted broadcasts. So actually, the title isn't complete, but it wasn't space enough. So I'll explain what it means. Let's just check my papers, because I'm starting to forget about it myself. Yeah, the basic assumption here is when you broadcast a message, it's actually not necessary that, it stands there, that the message reaches the whole network. Say there's 1 million nodes, you have something to tell the world and broadcast, you normally don't need to tell all 1 million nodes about it. It's enough that Normally it's more important that the node that is listening hears many messages. You want to have received 10 messages a minute. You don't want 1 million messages a minute. So that's the assumption. So what we do, for instance, with the Gnutella network and many other networks today, in the messages that you broadcast, you put a time to live counter. And you set it to some max number, and when it jumps across the message, each node is lowering the counter, and when it reaches 0, they don't forward it further on. That means you just reach a limited amount of nodes. That's the normal way to do it. But I find that a bit stupid. There's a better way. You can actually turn the counter around. Instead of counting down to 0, you can start at 0 and counting upwards. Not a big difference, but it makes a big difference. You see, if there's 1 million nodes, and there is only one node broadcasting, then of course you could broadcast to the whole network, no problem, because there's only one talking. But if there is lots of nodes broadcasting, like every node, then every node will get too many messages. What I do then the throttling kicks in. That is, you don't forward every message, just forward some. And you do it in a balanced manner. That is, you only forward the messages with the lowest jump counter. So that means, for instance, if too many nodes are, if say all 1 million nodes are broadcasting, and you're only allowed to forward 10 messages a minute, then each node, and you have 5 links per node, 5 incoming links. That means each node will only receive 50 messages, because the throttling prevents you from getting more. But you will get the 50 youngest messages, and that means that each node that is broadcasting will reach the 50 closest nodes. And everyone gets 50 messages, and that's usually enough in most cases. If there's only 10 nodes broadcasting in the whole network, they will reach the whole network, because everyone is accepting 10 messages a minute. So it balances. So it's just turn the time to live counter on and make around and make it a jump counter, and then it gets better. Yeah. Oh, and one more thing about slotted broadcasting is if there's different kinds of messages in the network, you should balance them individually, because if some kind of communications have lots of messages, it will drown out the other type of communication. So you should treat them separately to not drown out each other. Okay, here is a little what we can do. Everyone is thinking about file sharing and communicating, but there is other things we want to do. For instance, we want to count how many nodes are online, how many nodes are in the network. Every peer-to-peer network that I know of uses a server for that, even Gnutella networks. But we can do that in a distributed manner. We don't need servers for that. There's actually 3 ways to do it. I'm sorry, I don't have the time to tell you how to do it. You can ask me afterwards. It's very simple to understand how to do it. Another thing that would be nice to know is how many unique nodes per month. You know, some nodes connect an hour a month, and they get offline again, so they're a bit trickier to count, but you can count them too, without any central servers whatsoever. A bit trickier, and I don't know anyone else who has solved it except for me yet. Probably some more, but no one has written a paper about it yet. There is other things. We can network averages. Every node is announcing some kind of measurement. For instance, how many files I have on my disk, the ones I'm sharing. Then you can take an average for the whole network. There's several methods to do that without a server. Another thing we can calculate is the median value. That is, how many here know what the difference between medium and median? Can you raise your hand? Okay, I think many knows. I won't go into that. It's a slight difference, but I can also do max and minimum values. Very simple. Oh, sorry. What I cannot do, and I'm a bit ashamed of it, I can't do percentile values yet. It sounds simple, but I haven't solved it, sorry. Probably to take some months studying it some other time. I can do network totals. How, for instance, number of files total in the network or number of megabytes transferred in the network the last hour or whatever you want. That we can do. And we can agree on the network time. That is, all nodes can agree on what the clock is now within some seconds or so. That time might not be the real world time, but at least they agree about it. And that can be nice when you want to do logging and stuff. So logs agree. I should mention, all of these statistics, none of those can be done securely. All of the algorithms we have for this both my own and others, are not robust and can easily be sabotaged. Sorry, we haven't solved it better than that. But as long as most nodes are not evil, we can do it correctly. And actually, the median value can handle up to 50% evil nodes, and we can still get the right value, almost. But most of the methods are pretty vulnerable. But at least we can do it. Okay, here's one thing that's very special to me. It's what I call subnetting in peer-to-peer systems, or subgrouping. That is, when you start off a network, you need to be fairly many nodes to be able to find the network. You have to have a long start list to, hopefully some of them are online. If it's a small network, you can't get a long start list because there's not that many nodes. So when there is only 4 nodes in the network, you probably won't be able to find any of them next time because all 4 might be offline. So then it would be nice if several peer-to-peer networks could cooperate and connect together in a big network so they can help each other with the bootstrapping. And also some other things like network time and stuff like that benefit if the network is bigger. So sometimes bigger is better. And that means we can have a big mother net, and then we have one subnet, or separate net really, for each application. They can use the mother net for those things that needs to be done on a big network. So small networks can help each other out, and old big networks can help new small networks. And also old networks that are shrinking and becoming small networks because they're losing popularity can get help from newer big networks that are popular. So together we are stronger. And really each application subnet here is a separate peer-to-peer network really. It's not in the mother net, it's separate, but the node is working both in the subnet and in the mother net. And also here, there is something I call public subnets. Some applications want to cooperate, so they can start a separate subnet where several applications join that subnet to do whatever they do together. Here is a more well-known thing, what I call service subnets. Some call it a rendezvous service. I don't know how you pronounce it in French really. But it's the same idea really, but for a slightly different purpose. Within one application network, for instance, you want to have chat rooms. So nodes that want to chat with each other, they start their own little network. Only nodes in that chat room are in that network, communicating directly with each other. Because sending chat messages all over the main application networks would be a bit wasteful if there's 1 million nodes and you have to route a message long ways over the application network. So I create small subnets for that. And then there's a little extra thing you can do with this. If we have this subnet functionality, then we can use it for things like algorithms. That is, we tend to, well, 2 years later we have a better algorithm for our distributed database. So we want to plug in a new algorithm. And that's usually very messy. So what I do, for starters, I don't put the main algorithms, databases and stuff like that directly on the application subnet. Instead, I put them in a service subnet. So that means any node that is compatible with that version of the database, they join that subnet. And if we decide to be not backwards compatible one day, we create a new subnet for the new algorithm. So that means we can be future compatible. And of course, a new version of the software can join both the old and new database if we want to. Also, service subnets can be something else. It's not just chat rooms or swarms of nodes. For instance, if you use BitTorrent, you know what a swarm is? I would put a BitTorrent swarm in a service subnet, of course. Another thing that could be a subnet is a user identity. That is, a certain subnet can be one node. For instance, my username. So if you want to phone me or chat with me in person, a personal message, then you would look up my subnet and contact me. Because if you find my subnet, you know where I am and can find me. So there's many uses of subnetting. Just an overview. I have the mothernet on top, many applications in their own subnets, and under each application we have different service subnets. So it's actually a two-level thing, not one level. Yeah. The addressing, the address of a subnet is not the name of the subnet. For instance, we might have a chat room by the name CCC. And humans tend to choose bad names of subnets, names that collide in many letters. That would mean the address looks pretty similar. So what we do is we take the hash of the subnet name and we use that hash as the address. It means it makes the subnetting algorithm that we use to find the subnet better. And there's an added trick to that. We can actually also do secret subnets. We can take the name of the subnet, for instance, CCC, and the key for that room, the encryption key, or password if you want to, and we concatenate them, and then we hash that whole thing, and that is our address. So the address is the hash of the subnet name and the subnet key. And that means someone who knows or can guess the room subnet name, but doesn't know the key, doesn't know the address of the room, so they can't find it. And they don't know which of all the subnets, because they can see there are lots of subnets hanging around on the network, but they won't know which of them is that subnet. It gives you a little anonymity and security. Let's see. I'm just checking how much time I have on. It seems I almost have to skip some parts. Sorry. I should mention there's many ways to make the subnetting algorithm, how to find a subnet. I use actually throttled, balanced, slotted broadcasts for it. And what I do is I have on, for instance, the mothernet, each subnet announces, broadcast their existence. Every node in that subnet says, I'm here and I have this address. If you want to join this application, join me. Problem is, of course, we'll have lots of subnets broadcasting. So what I do is that I have one slot, one separate broadcasting system for each subnet, and all those are throttled individually. That is, of course, bad if it's 1 million subnets, because then it's 1 million slots. So what I do is I do top 16 slots on a mothernet, and if you need more than 16 subnets, then you do subnets under subnets, of course. So there are 16 levels below the mothernet, and below that, each of those levels, there are 16 levels. And in that way, you can work your way down to the correct subnet. That's just one way to do it. There's many more ways, but that's how I prefer to do it. So I'm actually using broadcasting for subnetting. If you know what a distributed hash table is, you can understand that it's almost like a distributed hash table, but it's broadcasting based. Oh, and the difference between this and distributed hash tables is that the node doesn't insert an item in a hash table. It actually inserts itself. It puts itself in that part of the hash table where its name is. So that's a difference, and makes it much more robust. Yeah, let's go on to another algorithm, or set of algorithms. It's broadcast searching. If you know about the Gnutella network and Kazaa network and many more, you have heard about broadcast searching, perhaps. It means you connect into a random network, for instance, or a small world network, and if you're searching for something, you just broadcast your search question. And it jumps around to many nodes, and those who have what you want send you a message back and tell, I have the thing you're looking for. The problem with this is, of course, if there's 1 billion nodes, and you broadcast to 1 billion nodes, you would be flooding the network if everyone is searching. So you have to have a jump counter or time to live counter. You have to throttle and balance it. And that means you can only search the nodes that are closest to you. There is a search horizon. A common search horizon is usually about 10,000 nodes. You can't search further than that because then it will be too much messaging going on, too much traffic. It uses lots of bandwidth, yeah. It's very good at handling complex searches like CCC and video and not Berlin. That is the kind of search question broadcast search can handle very well, because you're actually asking every node in person, more or less, by broadcasting to them. So they can really look in their local database and check what they have and do complex. You can even do reg expressions and stuff like that if you like to. There is some tricks to make to extend your search horizon to be able to reach more nodes. Yeah. And One very well-known method is supernodes. That is, some nodes collect information about other nodes, so they can answer not only for themselves but also for other nodes. In that, in one way, extending your horizon a bit. There is also another trick that's use a search filter. That is, instead of just having the complete copy of the database from a neighbor node, you just have a filter function. For instance, a Bloom filter is a very popular way to do it. That tells more or less what other node, that tells about what another node is. So you know if it's worth the effort to broadcast the message of the last step to the next node, if it's likely that it will be able to answer it or not. If it is not able to answer it, you won't send the message, broadcast the last step in the broadcast. So it can make it a bit more efficient. And then there is what I find the most efficient method. It's something we call mini groups, which involves grouping the nodes in big groups, and everyone in the group knows everything about each other. And then we can actually, on most normal file sharing networks, we could probably be searching 1 million nodes with broadcast search. That is, your search horizon would be about 1 million nodes. But we can't get it further than that, because then it would be too much traffic. Depends, of course, how much people are searching and stuff like that, but it's you can put 2 zeros extra on your search horizon. Yeah, now we're going on to the holy grail in peer-to-peer networking among researchers, at least right now. It's something they call distributed hash tables. I would prefer really to just call it a distributed database, because that's what it is. It means you organize all the nodes in some kind of address order. Here I've made it simple, it's just letters, but normally it's bytes, byte order. So you connect them. For instance, you could connect them in a long line, first node to last node, or you could connect them in a ring, or in a hypercube, or some other structured manner, but in address order. So each node will be choosing one address, preferably randomly, and insert itself in the right spot in the network. Usually we put them in a ring, for instance, because often nodes need to back up each other, because if a node disappears, the neighbors should be able to take over and take care of the information that node we're handling. So if you have it as a ring, the first and the last node can back up each other. You can't do so the C node will back up A node. Yeah. Now, if it's 1 million nodes, that ring is going to be pretty big. And if you want to look up something that is stored in one of those nodes, it would be very, very far away around the ring. So, of course, we're cheating. We put shortcuts across the ring, of course. That means if you want to look up some address, you can jump across the shortcuts and get to the node you want fast. Of course, it's not always like this. This is one of the more famous structures. Some are hypercubes instead. And the hypercube itself is actually those shortcuts. Those shortcuts are called a routing overlay, by the way, since we route messages along the overlay, or we jump across the overlay. So many current distributed hash table implementations do not have a ring, they just have the routing overlay. The distributed hash tables, they are not that good for complex searches like CCC and Berlin and not video. Because they're really good at looking up one item, a key. If you have a name for something, you can find it. But if you have several names for it, it makes it messier. So it doesn't work good. But we can do that, but it's not as well. So broadcast search is in some ways better, but in many other ways, this is much better. This means you have global searching. If there is one node among 1 billion nodes that has it, you find the item. And normally in distributed hash tables, you don't insert the whole item. If you have a video file of 1 gigabyte, you don't send the video file to the proper node that has the proper address. Since, say, your video file has the name A, you don't send it to the A node. Instead, you send a little announcement. You say that there is a file named A, and you can find it at this node, IP address, port number, encryption key to talk with that node. And you send that little announcement to the proper node, to the A node, and store it in the A node. So anyone looking for that file will ask A node and get this little announcement as response, and then can connect directly to the node actually having the video file. So that was distributed hash tables does. It's lots of research going on in that area because all current distributed hash tables are pretty bad. And one thing that is even worse is that no one have been able to do a secure one yet. We don't know how to do them sabotage-proof. We can do broadcast searching, pretty sabotage-proof. They're hard to sabotage, but distributed hash tables, all existing ones can be sabotaged, some very easily. So if anyone claims, and some universities researchers claim they have made secure hash tables, they're just a little less non-secure, but they're still very non-secure. Yeah, it looks like I'm on my last slide. Yeah. So if you have questions, now is the time, or afterwards, because I will be available afterwards. And as I say, you can ask in both English, German, or Scandinavian languages, if that's what you like. And as you noticed, I didn't went very deep into the things here, because I made it simple. So if anyone wants to discuss peer-to-peer networking and algorithms really, really deep, join me afterwards, and we'll get deep down and dirty. No questions? Okay. There's one question.
Are there any real-world chat serverless systems out there? Can I app-get install something right now which will be serverless for an IRC replacement?
He's asking if there is any serverless chat networks already available and deployed. And there actually are some, but most of them use broadcast searching on random networks. So they can only handle about 10,000 chatters in one network. So there's no really good ones available yet. So normal IRC is still, at the current moment, IRC is better than the peer-to-peer chat networks. But in like 2 years' time, probably peer-to-peer chats will be better than IRC, I hope. But there are some. But I have a bad memory for names. I don't remember the name of the current projects that has peer-to-peer chat.